Hi, this is Professor Fernandez, and this is Lesson 16's Video 1. So we're talking here about concavity and inflection points, and we will do that in the context of example 4.27 from Calculus Simplified. So let's go ahead and read through the example. This one says, consider the function x cubed minus 3x from our previous example in the chapter in the book. And then two questions, on what intervals is f concave up and down? And then also find the inflection points. So there are a few things to review here conceptually before we go off and find the intervals of concavity and the inflection points. So I've put down here the three pieces of information that we'll need. So I'll zoom in here for a second and just review those. So first of all, concavity. So suppose I have a function that's defined on an interval. We say that the function is concave up on that interval. I'll draw you a picture here. Concave up if the graph of the function is above, keyword there, the graph of its tangent lines. So in the graph that I've drawn here, if I draw the tangent lines, these are all below the graph of the function. Said the same way, the graph of the function is above the tangent lines. So in this case, the function f is concave up on this interval. If I kind of invert the drawing in a sense, I draw a function that's going like this, and then I look at its tangent lines. They are all above the graph of the function. Said another way, the graph of the function is below the graph of its tangent lines. Then this is a concave down function. So f is concave down here. Okay, so the pictures that I've drawn are not necessarily representative of what might happen. This is also a concave up function, right? So this one and this one are both concave up. So that's why it's a good idea to have some understanding of this concavity concept in terms of the graph of the tangent lines and the graph of the function on how they relate, right? Because you can have concave up decreasing, concave up increasing. You can have concave down decreasing, you can have concave down increasing. So these are all in the same separate category. So again, look at the tangent lines, whether they are above the graph, that's concave down, or below the graph, that is concave up. Great, so now that we've reviewed that concept, let's talk about how you might determine where a function is concave up or down. So the easiest way to do that, other than graphing it and maybe estimating it, but to determine the actual intervals is to use the concavity test. So suppose a function is defined on an interval I, then if the second derivative is positive for all points in that interval, the function is concave up. If the second derivative is negative for all points in that interval, then it's concave down. So there's a nice little way to remember this theorem, sometimes called the smiley face theorem. So if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down, right? So just a nice little visual way to remember that. Okay, so using all that, let's go ahead and do part A of the example. We will come back to inflection points in part B. So let's go up here. On what intervals is the function concave up or down? Okay, so we will employ the concavity test. This is also called, well, we'll just leave it at that, the concavity test. So I need to find the second derivative of the function. So I'll start first with the first derivative. So this is a difference of two power functions. This is 3x to the first, and this is x cubed. So I'll apply all the derivative rules that we've been talking about from chapter 3. So power rule here, 3x squared minus 3. And then I need the second derivative, so I'll differentiate that again. Once more, this is a power function, and then derivative of 3 is 0. It's a constant. So I get 6x here for my second derivative. Now, to find out where the derivative changes, or to find out where the derivative is positive or negative, we can use a very similar technique to what we were doing with the first derivative test. So we can create a sign chart. So the suggestion here is to figure out where the derivative is 0 equals 0 or does not exist. These are candidates for what we will talk about in B, inflection points, but they're also candidates for the points at which the function may change concavity from up or down, and therefore telling us concave up or concave down. So if I set 6x equal to 0, then I get x equals 0. So that's a point that we will put on our number line. If I ask where the function 6x does not exist, there's no such x value. If this were 6 over x, for example, then x equals 0 would be one such point. So really, x equals 0 is the only point x value here that belongs on our chart. And then what am I going to do with that? Well, kind of like what we did with the sign charts in the first derivative test, I'm going to pick x values to the left and to the right. And I'm going to substitute them back into f double prime. Which is 6x. And let's see what sign SIGN I get. So if x is 1, I get 6, so that's positive. And if x is negative 1, again, substituting it back into here, then I get negative 6, so that's negative. And then based off of the concavity test, I can then conclude that on the interval minus infinity to 0, because the second derivative is negative, the function is concave down. F is concave down on this interval. And then similar thing over here. So on the interval 0 to infinity, because the second derivative is positive, then the function is concave up. So F is concave up on this interval. Okay, so I have done the concavity part. So we have some sense if we were trying to draw this graph, right? If I tried to sketch the graph over here, we can see that at x equals 0, if I remove clutter here, at x equals 0, I have y equals 0, so f of 0 is 0. So there's a point on the graph there. And then we can also see that because I have now figured out the concavity, I know that the graph is concave up before 0 and concave down. Oops, sorry, the other way, concave down before 0, and then concave up afterwards. So, and the graph has to pass to the origin. So the graph may look, concave down to concave up, maybe something like that. So I don't know the details, right? The point of this question was not to graph the function. But the point of what I just did was to show you how information about the concavity, which we do now have, gives you some information about what the graph starts to look like. Okay, so let's move on to part B and talk about the inflection points. So having reviewed concavity, inflection points are a fairly simple concept from there. So here's the definition down here. So if I have a function, we say it has an inflection point at an x value c if the graph of f changes concavity as we cross c. So for example, here is a point. If it was concave down and then concave up, that is a point of inflection. However, if the graph is concave up and then continues concave up, that is not a point of inflection, right? So we want a change in concavity. So how would you find an inflection point? Well, you do exactly what we just did. So same procedure, find the second derivative. Okay, in this case that was 6x. Find where it is 0 or does not exist. Those are our candidate inflection points, right? 0 or does not exist. Does not exist. And we got just 0 for that. And then do the same sign charts as before, except using the second derivative to substitute these values in, not the first derivative, as we did in the local extrema content. And then at this point, you look back, you step back and you look at the concavity information you have. Notice that before 0, right, the concavity is negative, right? So the function is concave down. And then after 0, the concavity is positive, so the function is concave up. So as we cross x equals 0, the function changes from one type of concavity to another. And that's exactly what an inflection point is. So find the inflection points, x equals 0 is an inflection point. Inflection point. Okay, so we have answered all the questions that were asked. So as usual, let me just end the video by giving you some additional information, kind of summarizing what we just did. So first thing to know is that concavity, right, don't forget the definition in terms of tangent lines. Here is a graph that is concave up. Why? Because the tangent lines are below the graph. or equivalently, the graph is above its tangent lines. So don't forget that original definition of concavity. To actually find, where a graph changes concavity, we now know those are inflection points, or to just find the concavity on a certain interval, this is where the concavity test comes in handy. That involves looking for the SIGN sign of the second derivative, and you want to find points where the second derivative is either 0 or does not exist. Those are great candidates for inflection points and also x values that you put on your second derivative sign chart. And then, as in local extrema, you pick values over here and values over here, and you look at the sign SIGN. Is it positive to negative? Is it negative to positive? Or is it some strange setting where the signs don't change as you cross the x value? This will give you concavity information by itself, by the concavity test, and then looking at how the concavities change will give you information about the inflection points.